Hello together! As it says on the slide, I am Tim Düsterhus and I do a lot of sorcery involving HAProxy at Vault Lab. You might have also read my name on the mailing list before. Today I would like to tell you how we turned HAProxy's peers into an asynchronous and fault-tolerant quota tracker. At Vault Lab, we are developing Vault Lab Suite, a software suite allowing you to build online communities. We have been doing this for 20 years, since its first version in 2001. For the longest time, Vault Lab Suite was offered as a downloadable package for on-premises hosting only. Following a rising demand from customers that want a solution that just works, we began offering a fully managed software-as-a-service solution, Vault Lab Cloud, in the middle of 2020. With the origins of Vault Lab Suite dating back to the web forums of the early 2000s, our customers have come to rely on our software being very extensible and customizable. Our software-as-a-service offering should not compromise on this and offer an experience that is comparable to the self-hosted experience, but without the need to poke around the file system or database. This translates directly into some design constraints of Vault Lab Cloud that I will explain further along the talk. My talk is titled Using HAProxy Peers for Real-Time Quota Tracking. Let us first have a look into why we need quota tracking. Like many software-as-a-service solutions, we wanted to offer different plans based on the value you get out of our offering. However, the classic per-seat billing would not work well for us. In many cases, the registration in our customers' communities is open to the general public. Charging for all these users would result in the number of seats changing constantly. Charging for team members only does not work either. Due to the extensibility of our software, and the use of role-based access control, the lines between users and team members easily blur. Popular extensions for Vault Lab Suite include a shop software or a Craigslist-style marketplace. Customers are even free to uninstall the forum software we offer. Instead, we opted to reflect our real costs within the plans. These include the number of dynamic requests, as these increase the CPU usage within our application servers, and the amount of disk storage used, the latter representing an approximation of physical disk usage and bandwidth requirements. Both of these metrics are an appropriate proxy of the activity within a customer's community, and thus the value they derive. Of these two metrics, tracking the disk quota is easy. The storage used by a customer is not going to rapidly change, and it is persisted on disk by definition. To track the disk quota, we can simply query the file system in regular intervals, store the resulting number, and charge the customer for the peak usage within a given month. Tracking the number of dynamic requests, on the other hand, is definitely not easy. Requests can come in rapidly and can vary greatly depending on the time of day, especially during prime times. Furthermore, any incoming requests are ephemeral. Unless we immediately act on them, we are losing any record of the request being processed. So, how can we track these requests? Before we jump into the evaluation of the possible solutions, we have to take a moment to think about what we really need and what we do not want. The most important requirement is that quota tracking must not affect regular request processing under any circumstances. Tracking the number of requests is a means to an end. The customer is not interested in that, they just want their community working well. We had to find a solution that neither adds any significant latency nor gets into the way of the user. As much as the quota tracking is important for us, any failures must be entirely our problem and not have an impact on the customer and their users. Further, the tracking must not overcount the number of requests. It is simple. It is not fair for the customer to charge them for requests they did not use because we made a mistake. Undercounting, on the other hand, is allowed and it is unavoidable because of the first requirement. However, it should not significantly undercount requests if the system is working well. Customers should be able to rely on accurate usage metrics to be able to plan ahead. With the requirements established, we can now investigate how to implement this type of tracking within Vault Lab Cloud. To do so, we need to discuss the architecture of Vault Lab Cloud. Requests from the internet, indicated by the laptops on the right of my slide, come in via one of our HAProxy nodes. In Vault Lab Cloud, HAProxy is not so much acting as a load balancer, but rather as a router. Depending on the hostname, HAProxy forwards the request to the Nginx belonging to the customer's community. Having HAProxy as the entry point avoids wasting a public IP address for every customer, simplifies the setup of TLS certificates, and allows us to detect abuse in a central location. Nginx in turn either serves a static file, such as an image, or uses fastCGI to communicate with the customer's PHP workers. Every customer receives their own isolated instance of Nginx and PHP, as Vault Lab Suite is not multi-tenant due to its origins in on-premise hosting. After we discussed the requirements and Vault Lab Cloud's architecture, let us have a look at possible locations to insert the request tracking logic. One possible solution might be leveraging the access logs of the services and using them to derive the number of dynamic requests handled. However, access logs are inefficient as they can require hundreds of gigabytes of disk storage, and they also need to be parsed to extract the required information. For building purposes, they are also fragile as the scraper needs to carefully maintain any offsets to not count requests twice, or not at all. While in fact we have access logs for diagnosis purposes, they are also pretty detailed and contain personally identifying information. As such, they need to be deleted as soon as possible. This is at odds with billing requirements where we might need to preserve the data for the longer term. Conclusion: using the access logs of our services for request tracking is not a solution for us. Having ruled out access logs, I am going to move along the chain, starting at the application. The application could perform request tracking for us by installing a custom extension. However, our entire system is built as a zero-trust architecture. Trusting the application that, at least in parts, is modifiable by the customer to accurately record billing information does not really fit in there. If this was not a concern, there would be two options to perform this tracking within the application, and neither of them would work well. The first option would be storing the request count somewhere within Vault Lab Suite's MySQL database, and then regularly polling that value using the billing service. However, this option would greatly increase database load and I/O requirements, as the tracking table and its logs would be highly contended. The other option would be sending a ping request to a dedicated tracking service. However, performing external requests in PHP without blocking regular processing is hard. PHP's shared nothing model prevents the use of persistent connections, thus requiring TLS handshakes for every request. Performing non-blocking async requests is not really trivial with PHP either. Conclusion: extending the PHP application is not a solution. Immediately in front of PHP we have Nginx. For all intents and purposes, the open source version of Nginx is pretty much a black box when it comes to any sort of meaningful metrics. The available data is very limited and pretty much only covers the total number of requests and the number of currently established connections. There are no other data points that are of any use for us. The auth request module would allow performing sub-requests, but as the module name implies, they are meant for authorization. As such, the processing of the request will wait until the backend sends a response. Even worse, the access to the customer's community will be denied in case of failure. Clearly, using the auth request module for request tracking is not an option for us. Nginx also has support for Lua scripting within the request processing pipeline. It might be possible to leverage this to send ping requests to a tracking service, but we did not explore this in detail. A brief look at the Lua documentation did not yield anything promising in these regards. Conclusion: doing this in Nginx is not a solution. In front of Nginx we have HAProxy. However, HAProxy has little to no information about how the request is handled inside Nginx. It is entirely up to Nginx to decide how the path is to be evaluated using rewrites and the try files directive. As an example, we need to serve all static access directly from disk and forwards all requests for non-existent files to PHP. Conclusion: we can't do this in HAProxy either. Of course, I would not be here today if the previous conclusion was correct. While it is true that HAProxy does not know what happens with the request in advance, we can still provide clues afterwards. HTTP luckily allows us to communicate such information in band using custom HTTP headers, and that is what we are going to do. HAProxy also supports very efficient in-memory storage using stick tables. Let me give a quick explanation of what stick tables are for those of you who have never used them before, as stick tables are the core feature we are going to rely on. Stick tables are an in-memory key value store built into HAProxy. Each request may be tracked in multiple stick tables based on the key of your choice. Possible keys include IP addresses, such as the client's IP address retrieved using the source fetch, and also arbitrary strings. Within the stick table, several different types of data may be stored or tracked as the value. The arguably most powerful type of information that can be tracked is the request rate within a configurable time window. HAProxy is able to automatically calculate the request rate using the track key in the bucket. Another type that can be stored, and the type we are relying on for quota tracking, is the general purpose counter, or GPC in short. The GPC is a plain integer that can easily be set and incremented using HTTP actions. Of course, stick tables would not be of much use if one would not be able to access them from the outside. Luckily, stick tables are easy to extract using the stats socket. There's just one issue. As I said earlier, stick tables are stored in memory. As HAProxy never accesses the disk during operation, it is unable to persist them anywhere. And as HAProxy spawns new worker processes during a reload, the in-memory state of the old workers will be lost. This would result in unpredictably undercounting requests, violating one of the key requirements. This is where the peers protocol comes into play. By setting up peers, multiple HAProxy nodes are able to exchange stick table data amongst themselves. This is commonly used to share stick table data across the whole fleet, allowing each node to see the whole picture for abuse prevention purposes. Apart from allowing to share information amongst several nodes, enabling peers will also cause HAProxy to implicitly transfer stick table data to the new workers after a reload, preserving the current numbers. This got us thinking. If HAProxy is able to transfer the data elsewhere, why should we just rely on HAProxy transferring the state into the new workers when it can also transfer the state elsewhere? Is this the solution we are looking for? Yes, in fact we have found a solution that ticks all the boxes. Stick tables are a core feature of HAProxy, and they represent one of the foundations for HAProxy's ability to detect and to prevent abuse. They have proven to be highly reliable while not introducing any measurable latency. Being able to tap into a built-in feature made them the ideal pick for our use case. To top this off, incrementing a counter within the stick table is not going to fail, unless HAProxy itself fails. The stick table synchronization using peers is also handled completely asynchronously. If our tracking service goes down, HAProxy will not be able to send the updated counters, but it will not affect the main request processing pipeline. And with the tracking indication built into a response setter, we are only going to count requests when we actually send a response to the user accessing a customer's community. That's all there is to the theory, but how is this working out in practice? Let us look into the technical details. Adding the HTTP response header using Nginx is easy. We can just use the addHeader directive within the location block handling PHP requests. The always parameter indicates that the header should be added for all status codes, and not just the ones in the 200s range. Reading this header with HAProxy ACLs is also easy. Using HTTP response capture, we can augment HAProxy's access logs for easy verification that the response header was correctly processed. This allows an engineer to check the access logs to find out which type of requests used up the quota when the customer asks. As the response header is an implementation detail, we discard it afterwards to prevent this information from being leaked to the client. The customer ID variable and the backend name is not literally part of HAProxy's configuration syntax. Instead, it is inserted during HAProxy reload by our config generator. Defining HAProxy peers is also nothing out of the ordinary. We are using a peers section just for request tracking. All customers are assigned an internal 8-character customer identifier that we can easily reuse for our single quota table, using the identifier as the key and storing a GPC0 general purpose counter as the value. For the tracking service, we define a fake peer called tracker. The HAProxy configuration points to a closed port on localhost. HAProxy is never going to connect to the tracking service. Instead, the tracking service connects to HAProxy using tracker as its name. With the peers section defined, we can go back to the actions within the customer's backend. If the request was determined to be dynamic, we track it within the tracker/quota table using the customer identifier and then increment the value of the GPC0 counter within that table. HAProxy will then automatically broadcast the updated value to all peers defined in the matching peers section. In our case, this is just the tracker peer. And that is everything we need within our configuration. The remaining piece that is missing is the tracker peer that consumes the stick table updates our HAProxy nodes send. With Vault Suite being written in PHP and TypeScript, implementing the tracking service in Node.js using TypeScript was an obvious choice. We have created an implementation of HAProxy's peers protocol based on Node's standard library. This slide shows how the peers connection is set up with our library. We first connect to port 20,000 on the HAProxy node. In our production setup, this is a mutual TLS connection where both the client, our tracker, and the server, the HAProxy node, authenticate each other. After the connection is established, we pass the socket into the peer connection class that parses the incoming data and emits events whenever something of interest happens. In addition to the socket, we also need to pass the name of the two peers. The first one is the name of the tracking service that we defined earlier in the HAProxy configuration. That's the tracker literal highlighted in orange. The other one is the host name of the HAProxy node. It must match what HAProxy sees for the connection to work. Lastly, we bind a callback to the entry update event. Whenever HAProxy sends new data, this callback will be invoked. Within this callback, we can extract the modified key and its new GPC0 value from the update object. Further processing is left out for brevity, but we simply calculate the difference since the last update and then increase the numbers within the billing database appropriately. That is all there is to our quota tracking implementation based on HAProxy's peers protocol. The documentation of the peers protocol did not really shine here, and we uncovered a few, since fixed, bugs within HAProxy's own peers implementation. But we still managed to figure it out, and the resulting solution has proved to be absolutely stable. It required not a single change or fix since it went into production. As such, it definitely is our solution to quota tracking. Having an asynchronous, real-time and bidirectional communication channel built directly into HAProxy is a very powerful feature. For now, we are using this capability just for quota tracking. However, we have a few additional ideas floating around in our issue tracker. Most of these revolve around detecting specific traffic patterns to be able to quickly act on them without needing to pull the stats socket. Maybe you have already been able to think of something where this would come in handy while following along. I have good news for you. We are open sourcing our TypeScript implementation of HAProxy's peers protocol. HAProxy has been proven to be an essential cornerstone of Vault Cloud, and this is freely available as open source software. It is just fair to give back to the community and to share our results with you. Our TypeScript implementation is not fully featured and implements just the parts we need. However, it should be easy enough to extend or to use it as a blueprint for an implementation in another programming language. The repository also includes a simple demo configuration to easily try it out yourself. You can find it in the linked GitHub repository or by scanning the QR code if you do not want to manually type off the URL. That concludes my presentation. Thanks to all of you for listening in. Also thanks to my peers at Vault for assisting me in building this talk. I plan to be available for Q&A at the conference after this video finishes.
Another great presentation, and we have Tim with us live here. Tim, thank you so much for joining us.
Hello, thank you for having me.
So as a reminder to the audience, you can submit questions using the chat, as well as on Twitter using hashtag HAProxyConf. So we've already had a few questions here. We'll get right into it. So the first one, Tim, you built a stable solution for request tracking using TypeScript and Node.js. Why did you choose TypeScript and Node.js? Was it personal preference, or does it have some features that make it the better choice?
I already explained that shortly on one of the slides. VoidLab Suite is written in PHP and TypeScript, so we have the in-house experience with PHP and TypeScript. PHP is not really well suited for this type of persistent daemon running in the background, so using a TypeScript with Node.js instead was helpful because we know how it works. The ecosystem is mostly doing well, and with TypeScript, you have a programming language you can really enjoy using. So it's a combination of in-house experience and personal preference.
Sure. So thank you for elaborating. All right. So it's good to see that you're giving back to this open source community. Does VoltLab have any sort of history of open sourcing projects? And what would you say to encourage other organizations to get involved in open source?
Yes, we have a background in open sourcing our stuff. The core of VoidLab Suite is open source and available on GitHub. As I said at the beginning of my talk, our software is very extensible and customizable, and one can uninstall the forum software. All these apps, the forum, our gallery, a blog, and so on, is built on our open source core, which provides the user management and login functionality and basic CMS functionality, and everything else is built on that, and that core is open source. And we also contribute to other types of software, as an example, to the dependencies of VoidLab Suite. Whenever we find a bug within there, when I'm researching how to work around this bug, in many cases, this fix is very simple after you already found the bug, and then we can simply upstream our fix, and everyone can benefit from that. The same is true for our HAProxy contributions. I'm contributing to HAProxy itself. Most recently, a new feature for the HA-log tool to extract the captured headers. In my talk, I said we capture this plus or minus PHP header for the engineer to investigate whether tracking was correctly performed. I contributed a new flag to HA-log to extract these captured headers easily. That's what I also would say why one should contribute to open source. You can get your own features you wish for more easily or quicker. As an example, that feature with the header extraction, I requested that on the issue tracker several months ago, and now I simply implemented it myself, so we can benefit from this feature, and any future adjustments will be performed upstream by the HAProxy team in this case.
Yeah, well, that's very encouraging, and certainly a testament to the power of open source, and hopefully, your perspective there helps encourage others to continue to, contribute to the project or begin contributing if they haven't already. We did have a question that came in the chat. Could you give us more details about peer table issues in the current implementation?
I am not sure whether I understand the question correctly. What type of peer table issues is the person referring to? I said within my talk the implementation was a bit bumpy, but that was mostly because the documentation was more of a high-level developer reference and did not go into the nitty-gritty details of how to pass this peers protocol. So I had to look into the HAProxy code base to understand all the details with the state transitions and so on. So that was a bit bumpy, but now, as I said, it's working well. We did not change anything in the last 1.5 years.
So on that same vein, and you already answered some of this, but maybe you want to elaborate. While building out this project, is there anything that you wish you had known that would have made the work easier or faster for you and your team?
Yeah, not really. It's not like it took ages to implement this, and I was very familiar with the HAProxy code base, and there's not a single thing I could say that would have helped me to shave off 2 hours of the implementation. It mostly came along nicely with a bit of research in the C code base of HAProxy, but there's not something that was very important. It's mostly details. Yeah.
Yep. Thank you for that further explanation. So, and again, thank you so much for presenting on this topic. Are there any, do you have any parting thoughts or words for the audience? Anything else you'd like to share?
I don't think so. Let me just check the chat myself. Yeah, I don't think so. What Willie said, I really can encourage other companies or other persons to contribute to HAProxy itself, because you can improve the software for yourself and also for others, and you save off the maintenance that you would have to have for an in-house custom solution, because you can share the maintenance among a great crowd of multiple persons and experts.
Sure. Very, very fitting parting words. So Tim, thank you so much for your talk and for joining us here for the live Q&A. I hope you enjoy the rest of the conference.
Thank you.